Right, this is a lecture on matrices and forms, and it's on Sylvester's Law of Inertia. And we've got some examples and stuff. Right, first, the definition you might be asked for in the exam. This is where you say, you let V be a vector space and let Q be the quadratic form of V, and I'll show you how to find that in the next slide. Then there's a change of basis matrix P, such that P transpose times A times P equals this matrix here. And what this matrix here is this is the identity matrix, and then it's got algebraic multiplicity P, so it will be a P by P identity matrix, where all the values are 1. Here we've got a minus in front, so we've got R minus P number of them, of minus ones, and there could be also some zeros as well. So what this is saying is that V is now congruent to a matrix with either 1, -1, or 0 on the diagonals. Right. Some more definition stuff. The rank you should be asked for. This is where you take the number of squares that are positive plus the number of squares that are negative in Q. So you've got your Q is the quadratic form of V, so there'll be some squares in there. And to find them you just have to complete the square. Right, the signature, this is not really the same as the rank. This time we're adding the number of positive squares and subtracting the number of negative squares. So I think that with the signature is sign, so you do what the sign says. Right, and right now this part wasn't actually given to us, but I've just worked it out that if you want to find V from Q, then we find the coefficients that are in front of each of these things here. So down the diagonal we've got x squared, y squared, z squared, w squared, so on. Whatever's in front of that we put in this place. Whatever's in front of the xy, you have to divide that by 2 and put that there. Same for every other space. What we do here is we're linking up, so x and y meet, so whatever's in between x and y divide that by 2. Here we've got x and z meet, so xz divided by 2, whatever's in front, and yz, so got yz of 2, and it's the same here, so it's repeated there. So an example here is if we have 3x squared minus 4xy plus y squared, this will turn into this matrix. So this is the quadratic form of this matrix. So in front of the x squared we've got a 3, so we put 3 here. In front of the xy we've got -4, so we divide that by 2 and put -2 here. The same here, and in front of y squared we have 1, so it goes there. But I've just worked that out. Right, method. In solving these we want to complete the square. So here we've got they're not all squares. We want the quadratic to be only in the form of squares. So you complete the square. So if we were to complete the square here, then we get this, because we have to half this thing, take off the x. Leads to this, leads to this, leads to this. Now what we've done here, after we completed the square, we put everything in brackets that is a square. So we could have left it as 3y squared, but that wouldn't really be right for what we're going to do. So we have 3 times the y squared. Now we want to find the matrix P that we said about before. So what we want to do to find that is we want to find 2 linearly independent vectors v1 and v2 that multiply each of the square parts. We've got the x minus 2y and the y here, goes here, so that it equals x and y. And you usually do this by, you can usually do it by just looking at it. So the likes of, for this matrix, I haven't done it yet, but we want an x here, so we'll have v1 will start with a 1 at the top, and we want to we've got -2y too many, so we can have a -2 up here, so it'll be 1, -2, then we want a y, so I'd put 0 then 1, that'll work. Yeah, 1, 0, -2 and 1. Right, and then what you've got left outside the bracket, you want to multiply your final vector, v1 or v2 or so on, by 1 over the square root of this. And the reason it does that is if you were to actually put it inside the bracket, then it would cancel with the outside to get rid of it. And that's the way it's done. So we've got an example. We want to find the rank, signature and the change of basis of this, which is, we've got our quadratic form, which is x squared plus 2xy minus 4xz plus 2yz minus 4z squared. And first off, we're going to complete the square with the x part, so we get all the x parts together and it goes to this. Then this is what we've got left over too much. So we're going to subtract y squared plus 4yz minus 4z squared. And that's to just make it correct. Then we can simplify this by putting this stuff with this stuff, which will give us the minus y squared plus 6yz minus 8z squared. Then we can complete the square with the y stuff. So we put a minus in front because that's a minus y squared. Got the y. And because we put a minus in front, we'll have to change this to a minus. And we get 3z squared. This is what we need to change to make it correct. So we need to add 9z squared. And it will all go to this. So this 9z plus minus the 8z gives us just normal z squared. So we've got we've got 3 squares. If we want to find the rank, we have to add that we've got the total number of squared. So the rank is 3. And the signature, we've got 1 positive, 2 positive, and we want to subtract our negative ones. So the signature is 1. Right. Now we want to find the change of basis matrix. Remember that you get P transpose times your V times P. So again, we've got to get each of these linearly independent vectors, matrices, and we've got to multiply them to make that correct. Now the first, what we want to get first is the x, and this is the only place that an x comes up. So if we so we'll have to have a 1 here, yeah, because that will give us the 1x. Now what we've got is we've got one too many y's, so we want to subtract a y. So if we subtract one of these, so this one's going to start with a minus 1, and now we've got minus 2z, but we've also got plus 3z, so we want a minus 1 here to make that correct. So this line now only reads x for each of the top things that multiply. Right, the next one, y. We can start with this one, but if we used 0, 1 here, or anything, we'd get an x value and we can't get rid of it anywhere else, so we're going to have to start with a 0 there. And the same for down the bottom as well, because we don't want an x in the z. So we have to put a 0 there, otherwise we'll get an x value. So we want one of these now to get the y, but then we've got 3z too little. So we want to subtract minus 3z, so we want to add 3z. So if we just multiply this one by 3, that'll cancel it out and give us just the y as we want it. Now the last one, we just want a z, so it's got a y, so we want a 0 there, and we just want 1 because that's a z on its own. So these are our matrices here, our vectors. Now if we put these together, let's put them all together, then we get this matrix, which is the inverse of this matrix. And what this matrix is here, is this is just plotting x, y, z for each of these. So we've got 1x, 1y, minus 2z, no x, 1y, minus 3z, and just 1z over here. So you can do it that way, but I don't think you'll get as many marks. And also you've got to find the inverse of a 3 by 3, which is quite difficult. So I think this is much easier. Now we just want to check that it works. So we've got our matrix that we found here, and then we want to, if we find the transpose of that, which goes here, the transpose, dead easy to find, remember you just swap everything over, which is here. And then this matrix here is the one we found from the original quadratic. So using from here, remember it's whatever is in front of the x squared, which is a 1, half of this, which is 1, half of this, which is minus 2, half of this, which is 1, and minus 4 of this. And there's no y squared, so we put 0 as the y squared. So that's the y squared, which is 0, you've got minus 4, 1, and the rest of it's the same. And if we multiply that out, then we get this matrix here, which has the diagonals 1, minus 1, and 1, which is what we said at the beginning, that it will only have 1s, minus 1s, or 0s on the diagonal.